Thank you. I want to echo what others have said today, which is this has been a fantastic project, and I think it's sort of exciting to see the different pieces coming together. The thing about putting me right at the end also is that I think my talk I can make much shorter because I feel like a lot of the things people have already shown earlier today. I did want to acknowledge that. A lot of the things that I'm going to talk about today were the work of three of my students, led by them. So Jasmine, who is here, Sydney Dolan, who's graduated and is doing a postdoc at TU Munich, and Sid Nayak, who just graduated and will be moving to the Bay Area with Waymo. And you already saw, I'll probably skip through the part which was exciting. It's a collaboration with Jason Jingchi, Gabby, and at UC Berkeley along with Jasmine in my group. So I called it Learning Airspace Management. I think a lot of what we've been doing where we started this project was to take things up to the fleet level and the system level. And the motivation for much of this work really is beyond just the aviation context. It's that broadly in aerospace systems and certainly in autonomous aviation systems, there's a need now to manage better multi-agent coordination, whether it's search and rescue teams, which is one of the examples we've been looking at, or drones for environmental monitoring, or the advanced air mobility applications that we've been talking about for air traffic management. And then I should say that there's interesting parallels also on the space traffic management and the space-based surveillance side that I'll touch on a little bit as an extension of some of the work we've done, but I think I was just talking to Jason about it. I feel like there's much more that we could be doing with what we have learned on the airspace autonomy side from this project to space applications as well. The common characteristics that we try to address in the things, in this project is certainly multi-agent settings. Claire mentioned, we have these mixed autonomy teams right now. In fact, we're in this world where certainly the airspace is everything from fully to semi-autonomous to, entirely human teams or mixed autonomy teams. We're trying to make a step towards more and more decentralization, especially because when we have these on-demand applications that we're looking at, we have large numbers of vehicles which are operating from dispersed locations. So centralized planning may not be possible. Information constraint settings, there was a question from Krishna earlier this morning, but almost every example, when we look into more realistic deployments, we're looking at partial observability. We have certainly communication limitations, sensing limitations, and the environments are, if we're lucky, they're cooperative. More likely, they're non-cooperative. Hopefully not adversarial, but certainly increasingly, if you have AAM companies, competitive environments. And the thing that I will talk about in the pieces of the projects today is really that there's no free lunch. There's always going to be trade-offs between how much planning we can do, how much coordination we can do in a centralized manner versus in a decentralized manner, how large we can scale these systems to. Kevin talked about fairness as one aspect, so balancing load between different agents, how robust these systems are, how efficient these systems are, and information sharing. And really the goal for us is to try to come up with happy mediums which navigate these trade-offs. And that's the flavor of the things that I will talk about very quickly in the rest of this talk. I'm going to start with sort of the centralized view, because this was, I think, at the end of year one in the first talk I presented this. I'm not going to go into the details of this, but we started with exploring this idea of, we know we have trade-offs between efficiency and fairness in any of these systems where you have some sort of sharing going on. The example that we looked at here was we have, aerial sensing platform with a fleet of vehicles. So let's say we have 5 vehicles, 5 drones, and 5 customers who would like to do different things. And so the example here is we'd like to monitor traffic. We'd like to monitor parking. We'd like to keep track of cellular throughput over the region we're flying in, because we need that for beyond visual line of sight. we might want to do air quality monitoring, and we might want to inspect roofs. Each of these tasks is distributed across some region in the city. So the colors correspond to where each of those tasks are. They come in at different times. Maybe some things we want to do continuously. Other things are, the task comes in and goes away. And really, we are asking this question, how do we be efficient with our resources? So how do we share the available capacity on each of these drones in order to serve all of these different customers, but at the same time, not only serve one customer and entirely starve somebody else, so in an equitable manner. And this was a case where we're looking at, we have the ability to plan centrally. The demand is coming in, so it's on demand, but at the same time, we can coordinate all our assets centrally. But we're looking at this trade-off between fairness and throughput. What we then came up with as a solution was an online platform that could navigate this trade-off between throughput and fairness by sacrificing some fairness in the short term, but in the long term, try to recover and balance both throughput and fairness. And in particular, there was this question that's always there on what notion of fairness? How do you define fairness? And we considered maximum fairness. The math extends to a whole lot of different fairness functions. But I'm going to come back to maximum fairness as a recurring thing. So the idea of maximum fairness is we are trying to maximize the worst case service, the worst performance that any user is getting. And the nice thing about that here for us as a notion of fairness that we'll come back to is it's a measure of fairness that also looks at efficiency in that it tries to bound the worst performance of any of the users, right? So it's a good measure of fairness because it's something that takes into account efficiency as well. But in this case, what we did was try to convert this multi-objective optimization problem into a weighted vehicle routing problem. I'm not going to go through the technical details of this because I have done before, but what we were able to show is really that if you looked at just optimizing just for throughput, there's some level of how much performance you get, how much efficiency we get with the number of tasks that we cover. We could be very fair by giving each of our users one drone, but then that leads to much lower efficiency because sometimes you're just sitting around doing nothing if you don't have a task coming in. Whereas Mobius, which is our solution, actually by optimizing for maximum fairness, we can be quite efficient, right? We can get to within 10% of the efficient solution while at the same time serving our customers more fairly. So that was nice because we start with this, and there's certainly apart from being able to test this out on a real system, we were able to show that if we had this ability to coordinate all our assets, all our vehicles, then we can do this. We can navigate this trade-off between efficiency and fairness. What I want to really spend time talking about, for the rest of this talk, what if we really, in these systems, I said that we want to move to more decentralized approaches, solutions where you might have limited observations, so local observations and local communication constraints, where again, you want to navigate around obstacles and other agents, and you want to coordinate task distribution. All of the same trade-offs are going to exist. Can we actually learn to do some of this navigation using learning-based methods, right? That's really what we've been exploring since that first year. Where, I've talked about this before, and this is sort of the launching pad for this. In this work, which Informal, which sort of, kicked off in the group, the insight was that there is natural network connectivity that exists when we have these communication as well as sensing constraints. So we can build a natural graph structure based on the agents that we are capable of communicating with as well as obstacles that we sense. These are, of course, dynamic networks, but still there is inherent network structure, which then makes it very amenable for us to be using graph neural networks for information aggregation as a way to represent what is happening globally in the world. And so that was the idea. And so here, the task could be things like you have a certain number of agents who have to, either reach a certain number of targets or a coverage goal, any of those tasks, and we can come up with sort of scalable navigation and collision avoidance methods that only look at the local information and the information based on what you're connected to. So as I said, there's different types of things we could do. We could either have pre-assigned targets, or it could just be coverage tasks, which is similar to what Kevin talked about this morning, which we're exploring. Or maybe it's, you need to have all your agents form a circle or form a line between 2 points, equidistant and so on. And what we were able to show is that the informal, the method we propose, has very nice properties in terms of performance. The first is if we look at target task environments, and there's good transferability between training and execution for different levels, for different numbers of agents, right? So you can train a model with 3 agents, but then for both, whether, when you're looking at an execution, either 3 or 7 or 10 or 15 agents, the performance is fairly robust and it works reasonably well. Maybe even better for us is that the performance is actually quite comparable to RMA PPO, which is sort of the state of the art, but then assumes global information, right? So essentially what we have is the performance that we get from informal, which only uses information from its neighbors, each agent only uses information from its neighbors, is comparable to what we would get from RMA PPO using information from the entire, global information from everybody in the system, and also not having to retrain for specific numbers of agents, right? So we get really good performance in these different task environments. We then, as I said, there's the same problem that shows up in satellite systems as well, except in space traffic management, the dynamics are very different inherently. And so what we asked was, we can use the same thing where you have satellites that are trying to have, a rendezvous mission, for example, but the dynamics is very different. Do we actually benefit from using some sort of transfer learning from learning these tasks in the particle environments trained on the ground to the space-based environments, which have very different dynamics? And so in particular, these ground environments are decoupled, 2-dimensional decoupled dynamics, whereas in space, you have coupling in your dynamics, but also you can look at robustness to perturbations because of the Earth's flatness and so on. And interestingly, what we were able to find is that transfer learning is actually very effective here in that it accelerates the training and improves the performance of the policies. So here in this plot, it's comparing it to methods that use global information. So again, RMA PPO, which involves global information, but then we actually, the training performance is better when you initially, you train on the ground model, which is just, the simple dynamics, and then, space model is transferring that to the space environment. And in particular, what this sort of thing allows us to then do is to say we can evaluate the value of information sharing between satellite operators, right? What is the benefit of actually adding a communication link between 2 satellites and so on? So for us, it was nice because, as I said, there's nice parallels to the things that we're looking at into the space environment. The next piece, and this is closer to what, this is really what Kevin talked about this morning, is we can then think about, okay, how about learning fairness? So we knew from the Mobius work that there are between fairness and efficiency. And again, one way to look at this is in training, we can be training it on different types of assignments between goals and agents. So certainly we can be fair by being completely random, right? There's no bias there. We could be just training on optimal assignments, or we could be training on min-max fair assignments. And in particular, what we can then do is to also look at the coefficient of variation as another measure of fairness, which is try to make sure that you don't have huge variability between the distances traveled by different agents. And so the lessons that we learned firstly is the solutions, what the agents learn to do do vary based on what they're trained on. So this is just one example where agents start in the stop line and then they have to go, they're told to go to the goals here and figure out which goal they need to go to. They do different things based on what they've been trained on, whether they've been trained on a random assignment or they're trained on this fair assignment with fair rewards. But then the lesson really is, and that's good news for us, is when we actually train the models using these min-max fair assignments, they learn to navigate that the trade-offs between fairness and efficiency. So they're almost as fair as a random assignment. They end up being sort of reasonably efficient relative to the optimal assignment, right? So they learn to strike that balance between efficiency and fairness quite well. We can do this, again, going to different types of tasks. So, be fair and going into a formation. You can learn to coordinate to get into formation, but then do it in a way where nobody is taking too much of the load relative to the other, and so on. And so this is sort of showing the same things overall for different situations. I think the bottom line we want to take is typically in most of these cases, we end up with about a 7% hit in efficiency. The learned models that are trained on these max-min fair assignments are less efficient, certainly, than if you just purely learned on optimal assignments. But then you end up being much more fair by actually training them on knowing what fairness looks like as well as in training. So that's sort of the fairness and efficiency trade-off. I think there was a question this morning on, well, in reality, all of these applications you can't assume that your communications are perfect. So one of the things we've been looking at, and this becomes much more important with the space domain, is actually a case where you have very lossy environments or you have communication delays. And so recent work that I guess last month we presented at AMOS that Sydney Dolan read actually looks at using graph transformers to learn typical communication protocols and then adjust accordingly. And we find that even with 25% less reliable communications, you get fairly good performance if we can account for it while we are building out our policies. So not assuming perfect communications, we can recover performance as well, which, as I said, in some of these space applications become very important. The next piece, and this I'm actually not going to go into huge detail, but philosophically it feels like much of the same thing, where Claire talked about it. If we want fair safety, then there's two ways we can do. One is what we're doing with the combining work, right? When Kevin talked about it this morning, he said, well, when you add the GCBF on top of the fair mal assignments, you take a hit in terms of efficiency up front. On the other hand, I think philosophically the work here, that Claire's group and my group have been doing is, let's try to see if we can actually build that safety in while we're training it. And that way we get both the fairness, both the safety that we would get from CBF design, but then also puts the efficiency push that we get from the MARL methods, right? And what we are so I'm going to skip through all of this since you've seen most of this, but I'll go through you can't actually see the, okay. So I think this is the best thing to repeat what Claire said is, if we look at the safety blind version of the policies versus the safety informed versions, we see that we have fewer of those last minute go-arounds, right? So if we didn't, if we had to go through these waypoints, this agent actually gets here, realizes that for safety reasons, it's going to have to avoid all of these agents. And so it goes all the way around, then realizes it has to hit those waypoints, so comes back and then goes through those waypoints, which is incredibly inefficient. On the other hand, a safety informed policy does more proactive adjustment of the initial trajectories to be much smoother, which is what we see in these examples with merging flows as well, where you just have things which are much better strategic traffic management decisions than you would have if you waited to see the issue and then did it. So in fact, it does, I think this is work that shows that it is possible to learn the kind of proactive airspace management techniques that human controllers would use from experience, but then do it in a but then have automated autonomous agents be able to do that. The sort of the last piece is really going to the next thing that we need for AAM integration, which is, corridors are considered the way, these structured corridors. And so one of the, work which is ongoing with Jasmine is if we have the sort of corridors where you have to conform to the corridors, but also stay separated within those corridors, can we actually have agents learn to do merges into those corridors, splits off that corridor into another corridor in a way where it's more efficient than requires fewer tactical going in there and intervening to impose safety and so on. So much in that same flavor of let's get corridor conformance as an objective or some sort of structure conformance without sacrificing too much efficiency. So that's, the broad theme of, I think, where we've come from, where we started exploring these trade-offs, which we knew in these uncertain environments where we could do optimization, but then over the course, the idea was, can we move to learning-based methods to do much of this? And I feel like, yes, there's a lot that we need to do, but I think it has been this nice progression where we're sort of bringing in pieces from, and it's been nice to have the time to also bring in pieces that other people in the project have been working on, but then start saying, okay, how do we layer it into the Airspace side? And so far, I feel like it's been very promising results, which make us very excited because it feels like, in fact, we can get some of these objectives pushed up to the Airspace level as well. So with that, thank you.